All right, welcome back, Pre-Algebra. We are checking out exponents and division today. So we are working on the learning goal of applying the properties of integer exponents to create equivalent expressions. So this is a skill you will be able to do by the end of this lesson. So the first thing we want to review is that exponents allow us to write expressions that have repeated multiplication in them, but to write them in a way that's more efficient and more precise. So rather than listing out all of the factors individually like we have done here, we can list them out in kind of a shorthand way that's more efficient but more precise. It's easier for us not to make a mistake. So when we have the expression 7 to the 8th over 7 cubed, we can think about what that literally means and expand it to help us understand the rule for dividing exponents. So 7 to the 8th power literally means 7 is a factor 8 times. So I see 8 sevens listed here, and in my denominator, 7 is a factor 3 times. So if I begin canceling pairs of sevens from top to bottom, remembering that when I cancel, those simplify to 1. 7 over 7 is the same as 1 over 1. That's why I can do that. So now I see that I have 1, 2, 3, 4, 5 sevens left. So 7 as a factor 5 times over 1 would simplify to 7 to the 5th power. 7 remains our base, and 5 is our simplified exponent. So the shortcut then for 7 to the 8th divided by 7 cubed is to keep my base the same and subtract my powers, subtract my exponents. So I have 8 minus 3, which is 5. So we end up with 7 to the 5th power. Notice the order that I subtract these in is from top to bottom, and it's always that way no matter which power is larger. So when we are dividing powers with the same base, in arithmetic or with numbers, it looks like the example we just discussed. In algebra, or when we're using variables, it looks the same. We just keep letters instead of substituting in numbers. So a to the m divided by a to the n equals a to the m minus n. Now notice this doesn't work when our base equals 0. This is just for when our base is non-zero and m and n are integers. That's the only way that this rule or this property works. All right, so let's write some numbers from the box over here to simplify each expression. So if I'm starting with 8 to the 10th power divided by 8 to the 7th power, my base stays the same, and I'm going to subtract my exponents. So starting top to bottom, I have 10 minus 7, which is 3. So simplified, I would write 8 to the 3rd power. On letter B, I have y to the 13th divided by y to the 9th. My power stays the same, or my base stays the same, and I subtract my powers. 13 minus 9, which is 4. So the simplified way to write this is 9 to the 4th power. And finally, on letter C, d to the 20th divided by d to the 13th power. My base stays the same. I subtract my exponents from top to bottom. 20 minus 13 is 7. So I can rewrite this as a simplified expression of d to the 7th power. I think you guys have got it, but go ahead and pause the video and try this one quickly. As I subtract these powers from top to bottom, which I can do because they both have a base of g, 35 minus 23 is 12. So we could simplify this as g to the 12th. Nice job. All right, does a to the 12th divided by a to the 8th have the same value as a to the 6th over a squared? Well, let's simplify both of these and see if they both simplify the same way. So I keep my base the same, and I subtract my powers in order from top to bottom. A to the 12th minus 8 would be a to the 4th. And over on the right-hand side, I have a to the 6th divided by a squared. So I will subtract those powers. And I also get a to the 4th. So these would have the same value because they both simplify to a to the 4th power. So sometimes when we have exponents, we're going to have expressions that contain exponents but have a slightly different relationship. So we need a different property to simplify. So let's say that we have an expression like 3/5 to the 4th power. So notice it's not just the 3 that's in the parentheses, it's the whole fraction. So this whole fraction is being raised to the 4th power. So what that means is that 3/5 is literally a factor 4 times. In other words, 3/5 times 3/5 times 3/5 times 3/5. So essentially, in my numerator, I have 3 to the 4th power, and in my denominator, I have 5 to the 4th power. So I could rewrite this expression as 3 to the 4th over 5 to the 4th. Another way to think about this is that 3/5 to the 4th power is the same as 3 to the 1st power times 4 over 5 to the 1st power times 4. But for me, I think the simplest way to think about it is the way we have listed here. So we call this the power of a quotient. To find the power of a quotient, we can raise the numerator and the denominator to the power and simplify. So our previous example, we left this as 3 to the 4th over 5 to the 4th. But we could actually take this a step further and simplify. So if I were to do that, then simplifying 3 to the 4th, I would say 3 times 3 is 9, times 3 is 27, 27 times 3 is 81, and 5 to the 4th, 5 times 5 is 25, times 5 is 125, and 125 times 5 gets us to 625. In algebra, if we're just using variables and I have a over b to the nth power, then I can raise a to the nth and divide that by b to the nth power. So let's try it out here. This time I have a fraction in parentheses, but I already have an exponent, so I'm going to have to remember my rules for power of a power, because I'm going to take my numerator to the 3rd power. So that is a to the 7th raised to the 3rd power. So I can multiply because I'm doing power of a power. And in my denominator, I'm also going to raise this to the 3rd power. So a to the 7 times 3 would be a to the 21st power over 5 to the 3rd power. 5 times 5 is 25. 25 times 5 is 125. Now, if I want to double check my work here because this is confusing, then I can take this numerator here, a to the 7th, and I can write this out 3 times because a to the 7th literally means a times a times a times a times a times a times a. It means a is a factor 7 times. And I'm taking this whole numerator and raising it to the 3rd power. So I need this times itself 3 times. And if I were to write all of that out, I would get to a to the 21st power. So that's a way you could double check. Let's check out letter B here. I have 2x cubed over 3y, that whole quantity squared. So I am going to take my entire numerator, 2x cubed, and I'm going to square that, and I'm going to take my whole denominator, 3y, and square that. Notice I'm putting it in parentheses because the whole numerator and the whole denominator need to be squared. So that means each part of the term inside. So not only am I squaring my x, but I'm also squaring the 2. So I have 2 squared times x cubed to the second power over 3 squared times y squared. So as I simplify further, 2 squared is 4, and x cubed, and I have power of a power here, so x to the third times 2 would be x to the sixth. In my denominator, 3 squared is 9, and y squared is simply y squared. You guys are doing great. I know it's getting more complicated, but take it one step at a time and review your properties, and you can do it. All right, let's try this one. Pause the video, work it out, and then double check your answer. In the numerator, I'm going to get a to the 8th because I'm doing power of a power, so I can multiply them. In the denominator, I'm doing 4 to the 4th power, and then I have power of a power, so I get b to the 12th. Okay, so 4 to the 4th power, 4 times 4 is 16. 16 times 4 is 64. And 64 times 4 is 256. So for my final answer, I get a to the 8th over 256, b to the 12th. Super job. So let's review our key concept here. When we are dividing powers with the same base, we are going to subtract the exponents. So the key is to make sure we have the same base and it's not 0. And I can subtract my exponents. And when I'm doing power of a quotient, I need to raise the numerator and the denominator to the power and then simplify. Such as, 3/5 squared, I'm doing 3 squared over 5 squared. All right, you guys are ready to check out your 5.4 digits homework. Good luck.